Hi. So in this video we are going to briefly discuss the shapes of hybridized orbitals. So recall that, for example, in a carbon atom which is part of methane, right, CH4, the carbon atom actually makes 4 equivalent bonds. And so these bonds are all the same. They're pointing in a tetrahedral arrangement away from the central carbon atom. So this means that because normally a carbon atom has different orbitals, right? For example, the valence shell that has 2s orbitals and 2p orbitals, which look very differently as we have learned. These orbitals must be mixed together, it means hybridized, to form 4 symmetrical orbitals. And we're going to learn how this works. So we make 4 symmetrical equivalent atomic orbitals, which we abbreviate as AOs. Now, these 4 orbitals, they must also be equal in energy. Again, because of symmetry reasons. So let's see how this works with an atomic orbital energy diagram. So on the left here, we'll start to draw all the orbitals which a carbon atom has. That's a 1s orbital, 2s orbital, and 3 2p orbitals. And then we're going to fill in electrons. And we're going to do this here here what's drawn as an excited state, right? Because we have the lower energy 2s orbital. It's lower in energy than the 2p orbital. It only has 1 electron in it. Right, and normally we would fill 2 electrons. We would completely fill up the lower energy orbitals. Why are we drawing an excited state? It's just to show you how things can get hybridized more efficiently. So it's just kind of a way to draw this. So just remember what we're drawing here is an excited state. Now we're going to take all the valence electrons or the valence orbitals, so the 2s and the 3 2p orbitals, mix them together. It will be sort of called hybridization process. And first of all, then what we get is the 1s orbital, which is untouched. And then we get 4 equal energy orbitals. And those are the 4 degenerate sp3 hybridized orbitals. Right? And we fill in electrons. So then now all of these 4 orbitals have 1 electron in it, and all with equal spin to follow Hund's rule. Just definition here, degenerate generally means of equal energy. Now, what does this hybridization process tell us about the shapes of these hybridized orbitals? Essentially what we've seen is we've taken 1s orbital and one 2s orbital and mixed it with 3 p orbitals, right? So that means that the final resulting sp3 orbitals, they have 25% s character and 75% p character. That means an sp3 orbital looks mostly like a p orbital, so this would be a carbon, and here would be part of this sp3 orbital, but now remember in a p orbital that has 2 lobes of different color, one blue, one red, one positive amplitude, one negative amplitude. Now in the p orbital the 2 lobes are the same size, symmetrical, but now here with an sp3 orbital, because we're mixing in s character, one of the lobes becomes bigger. Okay, so this is the whole thing here we drew is a typical sp3 atomic orbital. And what I want you to remember is that one lobe is bigger than the other. So now we can take the 4 sp3 hybridized orbitals on a carbon atom and make methane out of it. It's a CH4 molecule. And how do we do that? We first, draw a carbon atom, and it has 4 directions in a tetrahedral fashion, where we're going to make the CH bonds. Now, if we draw in the orbitals, we're drawing in all these these sp3 orbitals, and they are arranged along these tetrahedral sites. Okay, so I'm going to shade the orbital coming forward a little bit to make it look a little bit more three-dimensional. And so now I put the 4 hydrogen atoms around, and we're going to draw in the 1s orbitals, which all have 1 electron in them, and for each hydrogen atom. And I see all that has to happen to form methane is we have to move the hydrogens closer so that the 1s orbitals of the hydrogens start to overlap with each sp3 orbital on the methane. Okay, and that's what happens here. So we are redrawing the system and forming all these CH bonds where the sp3 orbitals overlap with the s orbitals of the hydrogens. Here we go. That's a methane. Now, remember the thing, the CH bond, which is in darker blue, is in the front, the one in lighter blue in the back, and the angle here for the methane is 109.5 degrees, which is exactly what you always get for a perfect tetrahedron. Now, how can we use the hybridization concept to build a molecule which has a double bond? Something like ethylene, right? C2H4. Here in ethylene, we see that each carbon atom makes 3 equivalent bonds. Right, so we have a trigonal planar carbon atoms with 3 bonds. That means we must only generate 3 hybridized atomic orbitals. So let's see how we do that. We draw our atomic orbital energy diagram with 1s, 2s, and the 3 2p orbitals like before, and we fill in electrons like before. Again, this is the excited state, and now we need to mix up 3 orbitals. We leave 1 p orbital alone and take 2 p orbitals and 1 of the s orbitals and mix them together. And so this green 2 p orbital is left alone, so it's not affected by the hybridization, right? And the ones in the purple box are going to be hybridized. So we hybridize, 1s orbital is left alone, and the 2p orbital, the green 2p orbital is also left alone. So we just draw them again. And now we get 3 degenerate sp2 orbitals, right? And we can fill in the electrons like before. So that gives us the sp2 hybridization, and we can use it to now build something like ethylene. First, look at the geometry. Let's look at the geometry of these sp2 orbitals here on the right on slide A48. Essentially, we built a carbon atom. It has 3 equal energy sp2 orbitals and 1 unhybridized p orbital. Shape is very similar. The shape of the sp2 orbital is very similar to the shape of the sp3 orbital, except that now we have 33% s character and 67% p character. So a little bit more s character, right? And down here we are showing now, so we have these 3 sp2 orbitals. They're illustrated in gray. They all lie within one plane, and here we are at one in the back, one in the front, and one in the plane of the board. And then the p orbital, which was unaffected by hybridization, is shown in red and blue. Now we can connect all the bonds together in ethylene, and first of all we get sigma bonds, where we have head-on overlap, similar to how we formed H2 or methane. And so the sigma bonds are all shown in gray here. First one between the carbon atoms, between the 2 carbon atoms, then one a CH sigma bond, another CH sigma bond, another CH sigma bond, and the last one. Okay, so those are all the sigma bonds. Remember, head-on overlap. But then we also have pi bonds, which form basically through side-on overlap. It's the p orbitals are overlapping. And so here is the red part of the p orbitals overlapping and the blue part of the p orbitals overlapping. And so the whole thing is the pi bond, the red and the blue part together. We can of course draw a molecular orbital diagram for a pi bond like we did for a sigma bond in H2, and we would first draw an energy scale, then draw the two p orbitals of the two carbon atoms. You get a combination which is bonding and the combination which is anti-bonding. Like in the case for H2, we call the anti-bonding pi orbital we denominate it with a star, and the bonding one we leave the star out. So the bonding one gives, when if you fill that up with an electron, with electrons, that gives you a stable bond that strengthens the bond. If you fill up the anti-bonding orbital, it breaks the bond. So you see here we have two electrons, one coming from each p orbital, and we're only going to fill up the bonding orbital, the bonding pi orbital, with those two electrons. We leave the anti-bonding one empty, and so that's why we get a stable pi bond. Okay, the geometry of these orbitals of the pi and the pi star orbital, they look like the pi orbital, that you get constructive overlap, constructive interference, and like in the H2 case, you get destructive interference, where the signs of the orbitals are flipped with a node in between for the pi star orbital. So remember, red and blue regions are of the same molecular orbital but of opposite sign. So we can apply the same concept to hybridization in acetylene, which has a triple bond. So this is acetylene. And now here we see that each carbon atom forms two equivalent bonds. Bonds binds to two atoms, and so we must only generate two hybridized orbitals. Okay, we do that again with our molecular orbital diagram. Fill in the electrons. We leave two of the two p orbitals unaffected, and we mix one of the s orbitals with one of the p orbitals. Here are the electrons. We hybridize it. We get the first unaffected orbitals back, right? And then we get two degenerate sp orbitals. And here are the electrons, right? So then, analogous to the pi bond in acetylene, we can generate the bonding in acetylene. So here we now have the sp orbitals. They overlap head-on to form sigma bonds, like before. So here are the sigma bonds. The sigma bond between the carbon atoms, sigma bond between CH makes the CH bond, and another CH bond. So then, but we also have now two pi bonds, because we have two unhybridized p orbitals, or four in total, right? Two on each carbon atom, and they form two orthogonal pi bonds. So one pi bond is here, red and blue regions, all one pi bond. The other pi bond is here in the board of the plane. So practice these concepts, please, with Skill Builder 1.7. And thank you for watching.